Welcome to the third module. Today we'll be looking at cursors. To understand what a cursor is, first we'll have a look at the type of data that cursors apply to in terms of spatial data. So I'm just going to go to ArcGIS here, Module 3 Data Folder, Ottawa Geodatabase, Data Feature Dataset, Neighborhoods. So this is a spatial data file, a layer, a polygon layer, and every polygon here on this particular map has attributes. So for example, that polygon I just clicked on has the following attributes: object ID, names, block population from 2011, total dwellings from 2011, urban dwellings from 2011, a length, which is the boundary, shape area, which is of course the area of the polygon, and then something called n area and something called dissolve. Then I can open up the attribute table. The attribute table corresponds to that attribute data that I just showed you. Then in the attribute table, it corresponds directly with the objects on the map. So that row in the attribute table contains a polygon, which is a geometry, and then contains all of the attribute values for each attribute or column within this particular data set. Likewise, I'll click on the second one, and I can right click and zoom to that. Well, that's this polygon here, highlighted in blue. And all of the attributes that you see for that polygon are in this row in the table. And so if we want to access the data that's in the table for this feature data set, or we want to do anything with the individual geometries that are within this data set, we need to have an ability in Python to iterate over each row in this table. Because remember, each row in the table, because this is an object-based model, contains the polygon, the geometry, which is what we visually see on the map, and the attributes. And so the first row contains all of the information for that particular polygon named Barrhaven. And then the second row contains it for the second one. Now, the first one is Barrhaven, the second one is Beacon Hill South, the third one, the fourth one, the fifth one. And notice I can click on each one sequentially and see it highlighted on the map. And that row again contains all the information for that object. We can't see the geometry objects, the coordinates that make it up in here, but we can see that it's there. Now, what I'm doing with my mouse is iterating down over each item. And we can do that with cursors inside of our ArcPy. A cursor, therefore, is a way to go through and get each object on the map and its attributes. So we can manipulate them or change them or query them or do other things with them in the Python environment. The cursor then is a data access object. And as a data access object, it can be used to iterate over, so iteration, a set of rows in a table. And that could be a standalone table that has no geometry associated with it, or a feature class table, which we just saw as an example. Cursors allow us to get the information. We could even add more polygons with an insert cursor, and we can modify existing polygons, their geometry, and or their attributes with an update cursor. If we just want to go over them to get quantities or values from a particular table, then we use a search cursor. And notice the search cursor is read-only. So with a search cursor, it provides just the ability to iterate over each row or object in a spatial data layer and query or get the values of the geometry or the attributes. So we can manipulate them or use them in calculations inside of Python. The other two cursor types, the insert and the update cursor, allow us to make changes to an existing layer. The other thing to remember is that cursors only go forward. So once you initialize a cursor, and we'll see how to do that. Once you initialize a cursor, the cursor just goes forward through the table. It can't go backwards. So it's a forward only, and when it reaches the end, then the cursor can't be used again unless it's reset. And then you can go over from the top to the bottom again. So it's a unidirectional. Unidirectional iteration. And resetting cursors is important if you want to reuse them. You can either reset them or reinitialize them. The other thing to remember with cursors is if you're having ArcGIS open, let's say ArcMap or ArcGIS Pro open at the same time as you are creating a cursor in Python on a particular layer, if that layer is also open in ArcGIS Pro, it may not be able to do anything with it, particularly with update and insert cursors. And that's because of something called file locks. When an ArcGIS file is visible in ArcGIS and ArcGIS is open, then it locks that file for changes. And that's called a schema lock. So you can't actually modify it until you close ArcGIS Pro. So it's very important to remember that once a cursor is also opened on a layer, whether ArcGIS is open or not, ArcPy puts a lock on that particular file until such time as the cursor is removed through deletion. And if you don't do that, then you could end up opening up ArcGIS later, trying to do something with that file, and there's still a lock on it. And then you can't do anything with that file inside of ArcGIS Pro. So file locks are important because opening cursors locks a file for changes. And so you must be careful to always remove the cursor or reset the cursor after using it. And we'll see how that works as well soon. We'll see how to make a cursor and how to make a cursor in a way that it can be used and not have to manually be deleted or reset to remove the file lock. For an example, we have a table here, just like I showed you, the neighborhoods table. And we have rows. Each row contains both the geometry in the polygon, so that's a geom field. That's the geometry field there. And then the attributes. And it could have many attributes, it could have no attributes. But minimally, a layer has to have geometry to exist as a spatial data layer inside of ArcGIS Pro or Python. So the cursor starts with row 1, and then to row 2, row 3, all the way to the last row, only forward. And so we can reference or modify or query each row in the cursor as we move to it. So they only move forward through a set of features. It's again, I know I'm saying that a lot, but it's important to remember because you might want to have multiple cursors open in the same script. And you have to be careful to ensure that when you're finished with a cursor, either you remove it or reinitialize it. So if you want to reuse a cursor, you can use a reset method. That's one of the methods on a cursor. Cursors are simple things. They have two methods, reset and .next. So here's an example of creating a cursor, where the cursor then, the iterable, is stored in my cursor. And that's equal to arcpy.da, data access module, .search cursor. And here we specify the feature class that we want to iterate over, and then the field list that we want to iterate over. And that is a list of objects, or a list of names, field names, for example. It could be all field names or just specific field names that you want to go over within the cursor. Then we would have some sort of code here that does something to iterate over the cursor and doing things to it. So that's just imaginary right now. So imaginary code. After that code runs, then we reset the cursor. If we reset it, we can use it again down here, using the cursor a second time for the same data set rather than reinitializing one, rather than repeating this statement again. So once a cursor is reset, we can reuse it on the same data set. So let's look at an example here. This is an example of creating a cursor and then iterating over each row and printing the fifth column, values. So let's look at this piece by piece here. So the first thing we do is we create a field list. That list can simply be, in quotes, the asterisks. The asterisk means all fields. And strictly speaking, it's not a bad idea to put that in a list structure. So you always remember that the field list must be a list. But in this particular circumstance, when you specify all fields and you just give the wildcard character the asterisk right here, then that means all fields, and it doesn't have to be in a list object. So once we have the field list, then we initialize the cursor. argpy.da.search cursor, and again, this is just to look at the data or query it or use it, but not to change the structure of the file. 90% of the time, you're using search cursors. They're optimized for iterating over the objects or rows within a feature class. So we said the feature class FC, which is neighborhoods, and then the field list, which is right here, which would be just the asterisks in quotes. So that initializes the cursor. Once it's initialized, or a reference is stored in rows, rows is now an iterable. Just like a list, it can be used in a for loop. So for example, for each row in rows, and then each row itself is a list object. So that is a list with fields A to whatever, infinity. Obviously, we can't have that many, we can't have too many columns in a feature class table, but you get the idea. It's a list of values from the row, and then each subsequent row is printed. When we're finished, this is the important thing, to remove the locks. So once we print out each row, in this case, the fifth value of each row, so the fifth attribute value, that's just what's being printed there. Then once that's done, the next line after that loop structure is the deletion of rows, which is the cursor, to remove any locks on the files that could affect users down the line who might want to open that file and use it in ArcGIS Pro. Now, from here, notice I don't put all the opening code. I assume now that you can set the workspace and you know the imports that you need. So let's look at that example. We'll go over to PyScripter and we'll try it out. Delete that stuff that's in there, and I'll start by import ArcPy. So I import ArcPy. Again, this is the stuff that is assumed now that you know. Go to the next line, and then say from ArcPy import env, because we need to set our environment settings, especially the workspace, so we can work with neighborhoods. So I'll set my workspace, I'll say env.workspace equals, and I put my data in ctemp. So I'll just go over here, and in here I'll find my module 3 data. There it is right there. Module 3 data, Ottawa GDB. That's where the data is, so I'm just going to copy that. And I'll say the workspace equals R as a string literal now, and then in quotes, that path. So remember that when we have single backslash values between the path folders, we must put an R in front of that to make it a string literal, so that Python knows that this value is a literal value and not an escape character. And you know the other options, of course, are double without the R, double backslashes, or single 4 slashes. In any case, that works here. Now we have our workspace. I'll create my FC. I'll say feature class equals neighborhoods. Well, first I'll do this. I'll say, let's have a quick list here. So I'll run this. And then just down in the console down here, I'm going to say arcpy.list feature classes. So let's do list feature data sets first. So there's no feature classes directly in the geodatabase. So I'll say list data sets. So we have data and Ottawa data within our particular geodatabase called Ottawa GDB. So I'll list feature classes in data. So I'll have to append the path. So I'll say env workspace.workspace equals env.workspace. Let's use my concatenation operator plus, and then in quotes, another a backslash, I should say, data. Then I'll check my list feature classes. There it is, neighborhoods right here. So it's in the data feature class. So I'll copy that and I'll bring that up here and I'll say FC equals neighborhoods. So feature class equals neighborhoods. Then my list of fields, FLD list equals, and I'll take all fields. So I'll put that in a list, and in the list will be a simple thing with a quotation star. We'll also see how we can list certain fields later. For now, all fields are fine. And then I'll make my cursor, I'll just call it cursor, equals arcpy.da.searchCursor. And then I put in my feature class and my field list, like so. So I'll just run that to make sure it's running all right so I don't get any, there we go. So everything looks good. And if I look at cursor just in the console, I say cursor, it'll just say object. DA search cursor object at that. So cursor now is an iterable. So I can go under here and I can say, okay, and I'll just make I'll keep it tight so you can see everything. For row in cursor. So for each row in cursor, basically. And I'll just print. I'll print the whole row. I'll say print row, like so. So you can see that each one is a list. So now I'll run it. So when we run that and it prints out each row, you can see that each row is not a list, but a tuple is what is returned, I should say, a tuple. So it's an immutable list because remember, search cursor is read only. So in here it has 1, which is that FID field, the automated field that is put for each row. And then it shows us the centroid of the polygon in this case. So since we're not working with the geometry field itself right now, it just gives us a centroid of a polygon. And then the other attributes. And that's all one row. That's the first row in the particular neighborhood data set. Remember, it's Barhaven if we go back over here. So we go back up to the top. The first row contains those. 1, a polygon, which if we want to work with the polygon itself, we'll use the geometry. We'll see geometry next week. For now, the attributes after the polygon. Polygon is just shown here as the centroid, like so. And then we have object ID, 1, 1. And then Barhaven, right there, Barhaven. And then the next one is 17249. So that's right there, BlockPop 2011. And so every attribute for that row is there, and then the second row. And that corresponds with the second row right here in this table. Now, since a tuple is given back for each of these, we access it in the same way as a list. So let's say I wanted something particular from the first row, such as the 0, 1, 2, 3, the third thing, which is, of course, the fourth. So if I say print row 3, then if I print it and I run this, it prints out all the names. So each neighborhood name, everyone from that column right here, names, is printed out. And that's how we can access any value in the table using a search cursor. Looking again at the cursor fields property. So we can get a feature class. Once we get a cursor, there's a fields property on the cursor as well. So the methods again are next and up and reset, but the various types of properties on the cursor are things like fields. And this returns a tuple of field names. And then you could find a particular field location in there, the index value of a particular name, and print it out. So let's have a look at that as well. Why is this useful? Well, you can have something up here like you're searching for a particular name. Oops. Just go back there. You're searching for a particular field name like let's say block pop 2011, and you want to figure out, well, where is that inside the particular layer? Because you might be working with multiple layers called neighborhoods, and they may not all have at the same location or same index position the field of interest, because of the fact that there could be less fields in some, more fields in another. And so you're searching by name in this case to find a particular field that you would want, let's say, want to print out. So going back here, I'll just go back up here a bit, the cursor, and let's say the thing we're searching for right here, and I'll say field, search field equals BLK pop 2011, like that. So that's what I'm looking for. So I can get a names right up here, for example. I can say, okay, field name list equals cursor dot fields, like so. Then, just as we do here, we have the field names. I can get a field index using the index method of a list to get or find where the search field is that we're looking for. So I can say, okay, the index equals, and I just call it INDX in this case, field name list dot index. And then in here, I'm looking for the search field, like so. So now that I have the index of the field I want, I'll just put that in here for row. I'll say row, print row at index INDX. So that would be the block pop 2011. So running that, and then see how it just prints out all of the block populations for each single row. And of course, doing that, I could say, I also want names. So just a little bit expansion from what the slide says. Let's say I also want the name INDX, where the names are. So I could say FLD name list dot index. And then here, I'm looking for names. That's hard-coded at this point. Let's say I don't want it hard-coded, but I want it like this. So second search field equals names. And I'll just put that in here to be consistent. Second search field. And then I could print out the name and the population. So I'll down here in my print statement, I'll use quotes, open quotes, and quotes.format. And what's going to be going in here in the format will be the row with a name index. So row, name index, comma, row, INDX, which is the block population, and then the name. And so I'll put those in here. I'll say one squiggly brace, and I can put a colon, second squiggly brace to output these in a printed format. So I'll run that. And then I print out all these things, the name of the neighborhood, colon, the block pop. So by using search terms for the fields and using the index method of a field list, which is just names. So unlike, remember, list fields gives back field objects, which we have to then use the .name to get the name of the fields from the list fields, arcpy.list fields. The cursor fields property just gives field names. So a list of field names, not field objects. And then we can search that tuple or list for our particular field names, block pop and names, second search field. And then we can manipulate them in the cursor for each row. like we do here. In this case, the only manipulation we're doing is printing them out. But the print statement here represents code that would do something with the values usually, multiplying them, dividing them, using them in some other computation or whatnot, anything like that. So the print statement's going to represent here multiple lines of code working with the individual field values. There's different ways to look at this. So we can shorten the code. Right now we're doing this. So on the left-hand side, we're first getting the field name list, and then we're looking for the index of a particular search term to figure out where within the tuple that is provided from the search cursor for each row when you iterate over it. Remember, each row is a tuple, to find within that tuple where a particular search term is in terms of the index value. So we know where that field is, or the index of that column in the attribute table. Now we could just put those into one statement like you see here. Rows.fields.index names. That way we don't have to have a separate line for rows.fields, because if rows.fields right here returns a list, then the list has the index property. I should say the tuple, and has the index property, or that's a list, has the index property. And then you can just search for it right like that. So doing it this way just requires that you understand what is returned, what is the data type of the return here, and then working directly with the properties and methods of that return data type. And so we can explicit, so this is explicit here, and this is an implicit way. So implicit. So that's one way to shorten it. Another way you could do is you could say, okay, if names in row.fields. So you could use a conditional statement. And this has the advantage of first checking to see if names actually exists in this before it starts running the code here. And that makes it safer, because the code won't run if that particular field or search field is not within the list of fields. So that's a safer way of doing it, because what happens is, if we go back here, for example, and let's just say, I think it's name, and I run this, then I'm going to get an error. Tuple.index x is not in tuple. So it says here that basically the search field, second search field, name, is not in the tuple of fields, the field list. And since it's not in there, it just crashes the program. Instead, I could say here, I could say, okay, well, if second search field is in basically field list, cursor.fields, then go ahead and do this stuff underneath. Otherwise, it won't do anything. Now, if I try it, I don't get an error, and I just get nothing coming out the other end. So I could have an else statement here. Else print one or more of the fields specified is not in the attribute table. So one or more of the fields is not in the index table. So now when I run it, it specifies or tells me one or more of the fields specified is not in the attribute table. Now I only checked for one field here. So I looked for the second one, and I could look for two. I could say, okay, well, let's check that one. If that one is in there, and I could say then and then in parentheses, repeat this for the first search field, which is just search field in cursor.fields. So as long as they're both in there now, because I use the and, I'll just put that on a couple lines so you can see it. I'll put that escape character, just the line continuation character there, even though it's not necessary. So if the first search field and the second search field are in the list of fields, then go ahead and do this stuff. Of course, it'll still say that. If I put names back, then it will do the printing. If the first one, if I said BLK pop 2011A and I run it, I'll get that error. Tuple not in field. And why is that? Well, because I'm looking for the index value still outside the if statement. So notice here, the if starts here, and then if these are in the thing, then I get the index. Whereas I still have this one up here, which is outside of the if block. So I want to cut that and paste it after the checking. Because I can't get an index for a field that doesn't exist. It'll just crash the code. So now by putting it here, then everything will work out fine, and it will just say, well, one or more is not in the attribute table. And if they're both okay, and I run it, then everything works fine. So checking to see is very important, particularly in a script environment. So yes and no, let's say. In a standalone script, you need to check like this. If you're using a script tool, which we'll see later on in the course, you can set the tool up so that it only accepts fields. You're not going to end up with a situation where somebody chooses a field through the interface that's not already in the table of the feature class that was chosen for the analysis or the script to run. So that's something to keep in mind as well. The need to use these type of things, like an if statement here, depends on context. Now, going back to the shortening of that code, we got down here to rows.field.index, and we then used this one. And getting the index by field name is what we just saw. So, and this is just an example of what I just demonstrated. So we start by getting our neighborhoods, feature class, variable FC, and then the field list. We open a search cursor, and then we check to see if the particular attribute name that we're looking for is actually within the list of fields on that cursor. If it is, then it goes ahead and gets an index. And that's important because if we try to get the index and it's not in there, it crashes the whole program. Once we're satisfied that we got the index and everything's working fine, then we iterate over each row doing something or getting some sort of value. In this case, just each row and then printing the field index, whatever names was, wherever it is, so print out the names. And at the end, we delete the cursor right there. So notice here, I'm running this multiple times. I'm not deleting the cursor. And that's because in this particular circumstance, once it's done, it's running in its own space, but it still could be putting locks on things. So at the bottom, I'll just say del cursor, like so. And that ensures that that cursor is released and any locks are released on the file. It's an easy thing to forget, and that's why there's a better way to use a search cursor than doing it this way. And of course, using multiple fields in the cursor, we just went over as well. I showed you that. So here, we're using two search fields. Here I called it pop and S area to get shape area. And I look, is pop in there? So pop meaning BLK pop 2011. Is it in the rows fields? And is this one in the rows.fields? So I showed you that example as well, just in Python a few moments ago. And once we have those, we can look at them. In this case here, we're doing a computation. We're deriving something that isn't in the table. So we'll try that. Here now that I have this script written, I'm just going to make this a little bit smaller here, just to give more space to the code. I have everything already set up here for that, block pop, and then I have to look for, in this case, what we're looking for there, shape underscore area, like so. Then I can say here, down here, the population density of neighborhood is something. And then within here, I'm going to put a little continuation, like so. So you can see the whole line at once. Then row name stays the same, the name index. But the row IDX, or actually we won't have a name. We'll just say the population density is that. The reason we don't have a name is because we have just block pop and shape area being used as the search fields. So then I'm going to divide the index from the search field, so indx, row.indx divided by row, and then in slicing, name idx, like so. I'll remove that one from the dot format. So now it says the population density is whatever the value of row idx is, and idx is the search field. The search field is the population, right? So there's the search field's population, divided by row name indx. And that is, name indx is right here. And that's finding the second search field. And that's a shape area value. So if I run that, then I get, and I'll make that a little bit bigger here, I get the population density is this. Often, because population densities are small, we often look at them as number of people. You know, this is number of people per square meter, basically. So if we want number of people per square kilometer, so the shape area, we'd have to divide by 1,000 squared. So I put that in my computation here in parentheses. So row name index, and then we'd say row name index divided by 1,000 squared, like that. One too many, there we go. So I removed that X, I put an X parentheses there by accident, so I removed it. And now I have row IDX divided by row name IDX, which is again, second search field, shape area, divided by 1,000 squared. So that happens first. So first we divide the area by 1,000 squared to get area in square kilometers from square meters, and then people per square kilometer. It gives them more understandable meaning to population densities. And when you're doing it like in here like this, it can be a little bit more difficult to figure out. So why don't we do that in 2 steps? So I'll just call this pop equals row indx, like so. And then area kilometers squared equals row, and I'll just copy this stuff from down here, row 1,000 divided by 1,000 squared, like so. And then I only have one thing to put in here, making it more simpler to see. So this will be just pop divided by area km w, like at the very end. 3 separate statements instead of doing the calculation all in the dot format statement. Now that should work all right, great. So now you see the population density here in people per square kilometer is something that makes more sense to us. You know, we get something we can visualize or think about. And we can do that computation simply by the fact that we were able to reference the values in the layers cursor. Okay, so initializing a cursor with a statement, using a with statement, so to speak. So we create a cursor in this manner, and that's what we've been doing. The second way to create the cursor is to use this form here. So we say with the cursor, so with this part here, as the name of it, so as rows. So it's kind of inverting that statement. So rows goes over here. So you can see the pieces of that. So we say, we take this part here and we put it beside the with. We say with that statement, with the cursor, as rows. And rows is the name of the cursor. And that's just what that little blue arrow is showing there. So it's already there. Just wanted to highlight it for you. So it's just a kind of reversing the regular way we start a cursor, and there's no assignment in here. The assignment is made through the as statement. So we say with the cursor as rows. So rows is now the name of the cursor. We could also say with the cursor as cursor. And this is the preferred way to do it for a search cursor and an update cursor. So both search cursors and update cursors can be created in this way. And you're asking, why is that a better way? Well, this way, we needn't delete the cursor at any time. Because it's in a with statement, once the with statement, any of the code executed under the with statement is finished, the cursor is automatically deleted. Whereas this way, we have to say del, rows, like so. We have to delete it manually at the end. So doing everything in a with block, so to speak, with the cursor is better for that reason. Even if the cursor fails, it will remove all of the locks on any files that were being referenced to that cursor. So where we created the cursor then, we have something that looks like this. Oops. We have a with block instead up here with the cursor as rows or as cursor. In the example I was showing us, calling it cursor. With that as cursor, then we do everything underneath that. We get our field names, although those could be out here as well. They don't have to be underneath there, obviously. But anytime we want to iterate over the cursor, like this part has to be underneath the with block for each row in rows, when rows is the name of the cursor here. So going back to our example, we can just quickly change it. So up here, for example, I can say, instead of cursor arc, I'll say with this. Let's move it down here. With that as cursor. And I'll just bring cursor and drag it over here. As cursor, and then colon. And I'll remove the plus, the equal sign up there, the assignment operator. Then everything underneath gets indented in the with block, and we remove the del cursor because it's no longer needed in this form. So I didn't write any new code except for this one line. I remove the original cursor line. So that'll give the same thing when I run it. Oh, cursor is not defined. Oh, of course, yes. So since I'm searching, getting the cursor fields here, that has to be after the cursor as well. So first line after the cursor will be getting the fields. Then I can run it. And it runs the same, gives the same values. But this way, any locks that were on the neighborhood spatial data layer or feature class are automatically removed at the end of this cursor. Even if it crashed in here, it would still remove the locks. So that's the way we usually do cursors now, is as a with block. Accessing specific fields in the cursor, well, there's a couple ways we can look at that. What if there's more than two? So right now we have a case here where we say if second search cursor in cursor.fields and search field in cursor.fields, that's just for two fields, and that's becoming a fairly large statement. What if we have three fields? Well, we'd have, another and up here, and let's say, search cursor or search cursor, search field 2, let's say, in cursor.fields. Then I have another one there, and then I have my search field 2 up here. And I'll just set that equal to names as an example. Well, you can see that's becoming and I'll just make a bit of space here so you can see the size of that. So that becomes complex, doesn't it? We have two ands, so we'd have to, strictly speaking, want to parentheses around the first and operator. And then if that evaluates to true, and this one evaluates to true, then go ahead and do things. And go ahead and it works fine. But that's cumbersome for a lot of different fields. So there's better ways to do that. So first, we can get a list of field names and store it just as a field list right here. For example, we can get the field names beforehand if we want to just get them in a list before we use the cursor. So this is using the arcpy.list fields and then getting within a list all of the field names. And that's the way we have all the field names before we have the cursor. And we need to do it in order to check things before creating the cursor, for example. So up here, I have a field list, and it's just a tuple. In this case, it could be a list. Use a tuple or a list here for the field list. I have pop, block pop, and S area. Then I get a list of fields. And the thing you're seeing here is called list comprehension, this part right here. So let's have a look at just that part by itself. So here we have 3 fields, right? And we can put those into a field list. Search fields, I'll call them. So search fields equals a list or a tuple. I'll just use a tuple like the slide. And that'll be search field 2, and second search field. Not very good names, obviously, here, because I'm kind of building it as we're going along. So we have that list of fields, like so. And these are the fields we're looking at searching for. Then I get a list of the fields in the feature class using arcpy.listFields. So FC fields, or we'll call this the FC fields, field objects. So we know that those aren't names since we're using arcpy.listFields. And here, we want to list the fields in the feature class neighborhoods, like so. So we'll just put FC, as I was showing, like so, feature class neighborhoods. So that creates a list of objects. I'm just going to run this just so we can look at, again, the objects. So let's have a look at this right here, FC field objects, just to show you what they look like. Field objects. And again, that's a list of field objects, not field names, like you get from a cursor. Each object, which is a field object, has a property called name. So we can make a list of names. And we'll just call it, what were we called? Did we have a list of names before we did, I think, down here? Or maybe we didn't have a list of names. So I'll just make a new list here. I'll call it FC field list equals empty list. And then we'll add to that list each time. So in a loop, I'll say for FLD field in FC field objects, because it's iterable, it's a list, FC dot field list equals FC field list dot append. Append, it's a method, so we need to have that in parentheses. Dot append here the FLD dot name, and we'll just have it like this since we're appending. We'll just have it like that. So FC field list dot append field name. So it's going to increment or add to the field list, the empty one, each field dot name. So if we check out FC field list now, it has all of the different names in it, but it's a list of lists. So we need to fix that. We'll just append field.name like so. Not as a list, but just the actual name. So I'll run it again, check out that FC field list. And that's better. So it's making that bigger for a second. Now we have a list of field names, just as we would get from a cursor. But we need to have this list before we initialize the cursor in order to check first if our 3 fields are in that list. So that's why we're doing that. Now, I could just leave it the way it is. I could say second in, instead of cursor.fields down here, I can't even check that because I want to make sure that these things, so that each of the fields listed in the shapefile up here, which is our, let's go down a bit, our search fields, I want to make sure the search fields are in this list of field names before even initializing the cursors. That way I'll be able to remove all this part down here. I'll know everything will work. So that part I'll just remove for now, since I won't need it after this. And this needs to be outdented a bit. This part here needs to be outdented. So just like the little outdent up there we go. So it's right at the search cursor base. Okay, so how do we do that then? We could use, like the stuff we just deleted, each individual, search for each individual field in our list of fields, which is right here called the search fields. So we could look for each of these fields in the search fields, or I should say each of the fields here, not in the search fields, but in the FC field list, and use AND statements to put them all together. But that, again, is inefficient because it requires very, very long conditional statements. So the better way to do it is what we have here. So firstly, this is the way I just showed you. So I appended. We got our list of fields from ArcPy, which are objects. We created an empty list, and we said for each field object in the list of field objects, append to the field names here, just the name of the field. Now, in the code here, the way I did it instead is just with this one line. So I took all that and put it into one line right here, which says in a list brackets, so in the square brackets of a list, f.name for f in flist. Flist here being just the list of fields. And this is called list comprehension right there. So it's I already wrote it up there. List comprehension. Put it up there. List comprehension. List comprehension is a Pythonic, what's called a Pythonic way to create list objects without having to create an explicit for loop to go over and iterate over things. And it can be used with any iterable. So list comprehension in this form here, which is just the same as a loop for f in flist, right? So that's that part directly right there, except there's no colon here. And then f.name. And this just creates, without having to append or anything, each of the f.names. So if you just brought that under here, for example, f.name for f and flist, colon, f.name, that would just print out the names. In this case, instead of printing them to the console, it prints them into a list right here automatically. So then flist right here is the actual list of field names. So just before we go on, going back here, instead of doing this, I'll just say, what are we going to call this? FC field list. So I'll bring this down like so. I'll just copy it, or no, I'll deconstruct it to show you. So I'll put field list equals that, and then I'll make a list empty, and I'll say field.name. I'll bring that in here for, well, actually, I won't even put the for. I'll just take this stuff like that, and I'll take that and put it in here, deconstructing it. So fld.name for FLD and FLD FC field objects. And then we don't need any of this stuff, so we get rid of all that extra kind of, that's the dust that's left over afterwards. So the append is no longer needed. And we just need that one single statement to make the field list. And if we look at what's in the field list now, it's the same thing as before. So I'll just make that a little bit bigger, FC field list. So, and it's just a list of all the fields using the list comprehension way of doing it. So you should try that with a couple loops just to get practice with list comprehension. Although it's not necessary, it just makes the code more succinct and reduces the amount of time and memory required for creating lists, particularly large lists. Here, it doesn't matter if you use a for loop or you use list comprehension because there's only a limited number of names. You might have at most maybe a few thousand fields in a particular table, for most things. So it's not a big deal. You're not going to save a lot of time using list comprehension versus a loop. That being said, now we have that. How do we test for search fields inside here as an object? So we have search fields, which are a list of 3 field names. And we want to know if all 3 of those are found in this field list right here. And to do so, we do the following. Let me just go back a bit. We use the set function of base Python. So this creates sets, so logical sets. So we say set field list. So that's our list of all fields. I should say that's our list of search fields, field list. So set, and then in parentheses, our list of fields we want to find. We say dot is subset because a set creates a set object, and a set object has the method is subset of another set, which is the full list of fields. So going back here, before the with statement, I put an if. I'll say if set, and then here we want our search ones, so our search fields dot is subset of another set. It has to be another set here, and that set would be all the fields, FC field list, like so. If that's true, then do the with statement and everything after it. So I have to indent all these by 1. And this is a way that's much more succinct than writing out, is shape area in field list and names in field list and block pop 2011 in field list. Here we can take a whole list of things and test if it's a subset of a larger list. And that returns either true or false. If it's true, then it creates a search cursor and does our computations, which it will in this case. There we go. And we should bring the else statement out right there because it's if else. So we need to have the else statement out here. Then we can run it again and everything works as normal. If any one of these fields is not in there, so let's say I should shape areas by an accident, then I get that print that says, one or more fields specified is not in the attribute table. So that's these two things are very useful in flow control. Well, one in creating lists and the other one in checking for values within a list, multiple values at once. So with index, we can find a single value and its location. With the set objects, we can see whether or not a list of fields basically is in another list. So it doesn't compose a subset of it. So it's very useful code there. And that's just what's happening here. So that's why these keep getting longer, obviously, as we're adding some different things in here to try some different things. And then the list comprehension. Once you try a few list comprehensions, you'll figure it out. So once we then say if our search fields, field list, are a subset of the overall list of all fields. If so, go ahead and create the search cursor and do all those things. And here I'm just illustrating the difference between the Boolean statement, which we started with, pop in flist and sare in flist and names in flist, etc., all goes down to one single statement like that. Much cleaner and shorter. So more list comprehension examples. So we looked at name, f.name for f and f list, and we saw how I can deconstruct a for loop and just put the components in this list comprehension statement here. So it's always something, the thing in the list, and it's a property, or just the thing in the list if you want, for each thing in the list. So the variables are the same. You have your iterable, you have your for statement here, the loop variable is right there. And then you're just moving out, basically the idea is you move into that location any of the things you want that would usually be under the for loop. And these can be more complex examples like I show here. So with list fields, I could go and say, okay, well, I can do a couple things. I can get, for example, a tuple. I can construct a tuple or anything from the f value here, which is the iterable variable. That's the iterable. So I could say, okay, show me make each list component of the output a tuple containing the name and data type of the field. Or I can even put if statements inside of there to limit what things are compared here, or what values come out here. So I could say for f and f list, and then that if statement would generally be under a for loop. You'd say if f type equals some name, then include that name in the list, otherwise don't. So only including, let's say, fields of a particular data type. So if we go back here, right, just an example of this comprehension, which I'll do under here. Let's say I have a list that looks like this. So I have my list, and it contains, 12, 3.34.0, hello, because remember, lists can be heterogeneous things, 3, 5, and 9.0. So if, let's say, I want to filter that list down, and I only want things in a new list that contain integer values out of that. So integer values. So remember that if I look at my list now, my list, I just, well, actually, I'll just run this. And then I'll look down here and show you the values, the types, right? So we have my list is up here. And I say my list, 0, right? The first thing in the list is 12. Well, I could say, okay, what is the type of that? Type of that. One more of those. I think I'm type, yeah, it should work. But I need to put that up here, yeah. So I'll just try it again. Type of thing in my list, 0. Strange. Just check my list. Okay, it's there. So let's put in a variable x equals my list 0. Say type x, class int. Why won't that work with type? Type won't work, so it doesn't want to work with one of those. That's fine. So let's just say I want integer. So I know int is what I'm looking for. So then I could do this here. I could say, let's make an empty list, int list. So that would be the regular way of doing it. Int list is an empty list. And I'd say then here for item in int list. Not int list, but my list. In my list, next, int list, I'd say if item, right, type item is int, then in list, I want to call that int list. There we go, int list. And I'll say int list dot append, and then I'll append here item, like so. Int list, it's right there, right? I spelled it different. Oh, I see int list. I used camel case there. Int list, there we go. So now in int list, down here, it contains 12, 3, and 5, right? Because 12, 3, and 5 are the only integer objects in there. Instead, I could have written it as a list comprehension. I could say, okay, int list equals, and then the list thing, type, or just say item, for item in my list if type item is int, like so. So when I run that, and I look at int list, 12, 3, and 5. So I take this and put it into a single list comprehension statement with an if, so that only when the type of the item is int does it put it over here into the list. So whatever is over here basically is going into the list, and then the for loop is here. So that's the for that part, which is the same as right here, same spelling, but no colon. And then the second line was an if, and that's right here, but without a colon. And then this part is just that, automatically appending it. So list comprehension is very, very useful, but yeah, it's intimidating at first. The basic way to just try it in its simplest form like that to better understand how to use it. Here's a list comprehension way of doing our script. So we have our, again, everything here is the same as before. Different names than I'm using in the examples, but same thing. We have a field list. We use our list comprehension. And then we say if our search lists are a subset of the field names, and then we print out something here. So that's the previous code. That's just the previous code right here, this big thing. So that big thing there, list comprehension, turns out to be just this. And notice here the list comprehension is quite big. It's a list with a bunch of strings in it. Because remember, the first thing after the thing is this thing, so the printing. Each row, and then we say for each row in search cursor right here. Since the search cursor here gives back an iterable, it can also go inside a list comprehension statement. So you can see how the code can reduce quite drastically to this from, again, that. So a number of lines to a much simpler, cleaner set of statements. Now, generally, I won't be using list comprehension all the time, simply because it's not as intuitive as it's meant to be. So programmers will say it's the best way because it's so intuitive and easier to understand. Really, it's not necessarily easier to understand, especially for long statements inside of list comprehensions. Using structured query language within cursors allows us to reduce the amount of records that are returned when we open a cursor to selected records that we want to particularly see. For example, This is the same thing you do when you do a select by attributes in ArcGIS or ArcGIS Pro. You create a SQL statement, a select statement such as this: BLK pop less than 5,000. That means return all of the records where the population field is less than 5,000 for each individual polygon or record. So that's called the SQL select statement. And we can use that within a cursor to get only records back that we are interested in doing something with. Now, before using a SQL statement within a cursor, we have to ensure that it is generalized for all data types. Unfortunately, in ArcPy, as in ArcGIS, there are different types of spatial data layers. So for example, if you're using a file geodatabase, a shape file, an ArcSDE geodatabase, an IMS feature class, there's all kinds of different ones you can use. And these ones up here require that you specify the name of the field as such, in quotes, area. For the now defunct personal geodatabase, there's still some around, you need to enclose the name of the field that you're looking to use in an SQL statement in square brackets like that. For file geodatabases, you can omit anything around them and just use the name of the field within the SQL statement. And so you have to either know ahead of time what type of data your script will be working with. For example, if it's always file geodatabases, you could create SQL statements like that. Area, let's say, greater than 500 square meters or something like that. And you specify the field name with no delimiters around it. However, you can't be sure that every layer that you use or will be used with your script will conform to a file geodatabase format. It could be one of these things up here. It could be this thing. It could be some other things. And so because of the different ways in which fields must be delimited, that means the things that go on each side of the field name, because of those differences among different data types, ArcGIS and ArcPy, well, ArcGIS doesn't offer, but ArcPy offers a add field delimiters function, so that no matter how you specify the field, it will add the correct delimiters for the data set it will be used on with an SQL statement. Here's an example. So let's say it's block pop 2011. Here I have single quotes around it. So I use the ArcPy function, add field delimiters, which takes in the feature class that the SQL statement will be used on, so that ArcPy knows what the feature class type is, and then the name of the field, like pop. And it automatically puts in the correct field delimiters and saves that in pop right here. And notice I'm just recycling the same variable twice there. And then that goes in here in the SQL statement. I say pop plus the concatenation operator, and then in quotes, the rest of my query string, so that condition. So with those conditional operators, less than, equal to, which are inequality. Then I can add this within my query, within my cursor statement right here. I can put SQL in there. Here's an example with using that in a search cursor. So my feature class is neighborhoods. I have a pop field, block pop 2011, and the name of the polygon fields, names, and I'll get those. And these will be the ones I put inside the cursor statement. So I just get two fields back. See it down there a bit. Then the one I'm going to use to reduce the number of records is the block pop 2011. So I only want records that specify a certain thing. And so pop then has to go into the add field delimiters down here. So here's the add field delimiters function, takes the feature class and the population, and then saves the properly delimited field for that type of feature class within the pop del variable here. So it knows that, and by knowing that, it knows how to delimit that field called pop, which may be different than single quotes. So when I use pop del now, which is that properly delimited field in my SQL statement, I say just that plus, and then in quotes, the rest of the statement, less than or equal to 5,000. Now I can open my search cursor. Now, even though I'm not using all of the things I showed you on the previous slide, such as checking to see if those are actually in the table and everything, that's assumed. So I'm just leaving those out now for sake of brevity in illustrating certain concepts. It doesn't mean that you don't need to check whether or not the fields are in the table. You should, but I'm not showing all that here because it would just make too big of a slide to try and show you all that code. So assuming that's all done in here somewhere, where you check the fields, see if they're in the table using the set notation, then you say with ArcPy search cursor, feature class goes in, and then you have to put in, since I didn't create a field list by itself up here, I just created a tuple right there. That can be a tuple or a list of the two fields I want, polyname, names, and pop, which is block pop. Notice I'm not using the delimited field within the search cursor here. Delimitation only applies to SQL statements. So after that, I put the SQL as rows. And so it's only going to return to me the objects or rows in the feature class table that correspond to populations less than 5,000. And I just printed out here to show that. So let's try that. Import ArcPy from ArcPy, import env, env.workspace equals, and I'll just grab the workspace from the previous one right there. Same geodatabase, same feature class too, so I might as well grab that just for brevity here. So env workspace is set, my feature class is set, and then I need to make my lists of fields that I want to work with, and I'll have one called pop. And that'll be equal to blk pop 2011, and then names or I should say NBR names, or what do we call them in the slide just to be consistent there? Polyname. So polyname equals names, like such. So now I have these two things, and I want to create an SQL statement based on the population right here. I want my SQL to say where block pop is less than 2011. So first I have to make the delimited field, and I'll just recycle pop. Or no, I need to use that again, so I won't recycle it. I'll call it pop del for delimited equals arcpy.add field delimiters. No, not that one. Add field, arcpy dot add field delimiters. There we go. Feature class FC, and the pop, which is holding the string block pop 2011. Now I can create my SQL statement. I'll just call it SQL for structured query language equals pop del, and I can use my concatenation operator here, and then I'll just use space here, less than or equal to 5,000, like so. So I'll just run that right now to show you what SQL looks like. So then I'll go back down here, I'll just type SQL, and that's what it looks like. So it delimited it for this data set in a double quotes. So the query statement is a string, as you can see here. So the string is specified by the single quote, the single apostrophes, and then the quotation marks block pop less than or equal to 5,000. Now I can use that in a search cursor. So again, I'm just skipping the part where we would usually now test whether fields are in the table. And then after that, we would have our, somewhere within that nested if statement, we'd have with argpy.da.searchCursor. And in here, my feature class, I'll put in my field list, which is pop, and I'll put polyname and pop, like so, comma, SQL as cursor. So that's the fields. So those fields will be returned as long as they meet the condition within the SQL statement right here. Only where the pop is less than 5,000 will records be returned. Then once I'm past that, I can say for row in cursor, now I can print out here. And again, here I could do anything. I could have any sort of code I want that works with the selected records. But here I'm just going to print them out to show what that looks like. So I'll say print, not capitals, of course, print, and then I'll have a regular format statement. And I have name and thing. So I'll say that has a population of that squiggly brace. I'll say dot format. And then in the first one, row, since the order they're in is polyname pop, in each row, there will only be a tuple with a polyname, the name of the neighborhood, and the population. So I know the order is not going to change here since I've hard coded in this particular list. Hard coded means it's actually, it's not a list variable, but a list made at the time of the search cursor. So it's hard coded in there. So that means I can ask for them by order here. So in the first one, I want the polyname. So I'll say row 0 and then comma row 1 for the second position. And that will print those out. So running that, you can see prints out, Kinburn has a population of 1870, North Gower has a population of 4,967, etc. And so that was successful. You'll see nothing there more than 5,000, right? So you can see in the numbers here, none of those numbers are more than 5,000 because all we asked for were neighborhoods with a low population or population less than 5,000. Doesn't mean necessarily it's low, it's just less than 5,000. And that's easy to change here. I could say, okay, less than 2,000. And they're all here. If I wanted to count how many there were, well, I could just, instead of printing here, I could have everything put into a new list, for example. Then I could count the list, right? So I could say, okay, before I open the cursor, let's make a blank list equals that. And then here, I'll use the print statement still, but I'll also do this. I'll say blank list dot append, and then row. Then at the end of my script down here, I could say length print length blank list. No, not there. Length blank list. It's not blank anymore. So I put the list here, empty list, and then in here I append to that list each of the rows, because all I want that for is to get the length, how many things were selected. Like so. At the end, after the thing, I can print the length of whatever's left in blank list, which is how many things met that condition of less than or equal to 2,000. So there we go. And that was 11 right there. It just prints it out. I didn't put any fancy format statement there or anything. You can see it's far less. So these are all the ones less than 2,000. Now, for more complex query statements, I suggest that you use the format statement up here. So let's say I wanted to get all of the records returned where there's between 2,000 and 5,000 people. Well, that's difficult to do here because I'd have to do this. I'd have to say, okay, I'll show you it. There we go. A parentheses plus all that. And I have to put end parentheses in there. And then I have to say and space open parentheses. Then I say plus pop del plus quote. So between, so I want greater than or equal to 3,000, or I want less than 5,000, and greater than or equal to 2,000, like so, and then an end pop in there. So that gets a little complicated, doesn't it? Because you have to remember all these little things like the open parentheses and how it's structured in the middle. It's much easier to do in a format statement, but I'll just run that to show you. So there's 36 in total. All of these values that you see here will be between 2,000 and 5,000. Oh, wait, something's wrong there. We got one worth 78 here. Let me just check the SQL. Oops, Python interpreter, SQL. So you have block pop that and block pop greater than. So we'll just switch them around here. The first one is greater than equal to. Greater than, no. Yeah, greater than equal to 2,000. Put them in order here. And pop del less than equal to 5,000. I'll run that again. Still gives the incorrect. Oh no, is that correct now? That's good yet. So no, it's not. So that SQL is having problems. I'll try just to rewrite it in SQL here in a dot format statement so I don't miss anything. So that makes it a little easier. So I'll say here, I'll say open parentheses, squiggly brace, greater than equal to 2,000, end quote, and open and close parentheses, squiggly brace, less than or equal to 5,000. Dot format, pop del, pop del. Because pop del goes, the population goes right into both of those. Let me just run it like that, see if I get the same thing, same issue. So why am I getting that? I'm saying right here, pop greater than 2,000 and less than. What if I try to spell it out? Probably that won't work. And 25. Okay, that's better. So it didn't like the ampersand. That needs to be and for the SQL statement. So now they both should give 25. If I close that one, I should say commented out and I run it, 25. And all of those are between 2 and 5,000, as you can see. So it was a matter of I was using the ampersand operator. It doesn't like that, so I had to use the and name itself, which is better in SQL. Now you'll also see here that out of the two statements, this one is more complex and it's easy to forget something in there. So if we get rid of that and we just use the format statement, that's a much cleaner statement because all we have to do is specify where our query field names go. And they go there, and then we just stick them in the format method. Of course, we could have used list comprehension for that. So there's a couple places there where list comprehension could be used. So this is the previous one. So this one right here. And again, just watch this part in particular right here. That then becomes that. Certainly more difficult to figure out what's going on there because you have the big format statement here using the row, and then for row in search cursor with the SQL. So that's more succinct, but more difficult to follow in that case. Next is update cursors. So update cursors allow us to update existing data within the table, whether that's geometry or attributes of a field. Here's an example. We get area, I should say neighborhoods again. Pop is an area. We're not using an SQL, so there's no SQL being used here. And we say with argpy.da update cursor, and it's the same arguments, feature class and the name of the field as rows. And then for row and rows, I say, okay, row 0, since I'm, which is here, is the n area field, so the n area field. So update row and rows, and then for each row, since I'm only asking for one field coming back here, and that again can be in a list format, so it's good to probably to keep doing that, even though I don't do it on the slides all the time. Put that in a list format, and then we say, okay, existing row 0, which is that item's value and area's value for the first record, equals the current value divided by 1,000 squared to make it into here area to kilometers squared from meters squared. So we do that, we write row 0. Now, nothing happens to the original attribute table until you call the update row method and send row, the current row, to it. So you have to say rows.update row and then row. And again, that's just that thing there. So it knows that it's updating that particular record. And then it changes it in the actual shapefile. Only once it's completely run. So once it's completely run and the cursor is released, then it will save the updates. So you won't actually see anything updated until the cursor is finished going through everything. Or if you use the cursor as with a variable, such as rows equals argpy.da.search cursor until you delete the rows cursor. So as an example here, back in here again, we saw this example here. I'm just going to make another one. I'll keep the same stuff here for now. And I'll just make a new fresh one, delete what's in there, paste that stuff. So neighborhoods, and I want an area. And I won't call that pop, I'll call that the area. No, that's I want to call it area. AR, area, poly for polygon. Or that's actually not a geometry one, so that's just area field. So that's a person-made field. And I might just list the fields in there first to make sure that's there as well. So I'll say argpy. I'll just do a quick list of fields with list comprehension here. So I'll say f.name for f in argpy.list fields. And here we need the feature class, fc. Then down here, I'll just check what the contents of f.name is. I did not run that. Oh, I need to save that obviously to list. Here we go. If I don't save it, I can't see it. List. So there's list and there's n area in there. So f list for field list contains all those there. So it's in there. So I want to use an update cursor to update the values. First, I'll look at the current values. So I can look at them with a update cursor as well as a search cursor. So I'll just make my update. I'll say with argpy.da.update cursor, fc for feature class, and then I'll put the list in here, area FLD, like so, as that, and then I'll say for row in, well, I need to put as up here as cursor. I'll say for row in cursor, print row 0. So the only value in the tuple. since the tuple that's returned by the update cursor only asked for one field, it will just have one value at index 0. So there's the big value. Those are quite big values, aren't they? So I just used that as I would a search cursor, but now I want to update them. So I want to say, okay, take this value, divide it by 1,000 squared, and save it back in as the new value. So to do so, it's pretty straightforward. Instead of printing here, I'll just say row 0 equals row 0 index times 1, or divided by 1,000 squared. Oh, we need the two things there to make it squared. You could also use the pow, math.pow if you wanted there. So you could also use math.pow and then row 0 squared like that. Either way, does the same thing. This is just a quicker way to do it with the double asterisks. Now I must do an update cursor. So I say, I should say I have to update. So on the cursor, so I have to say cursor dot update row, and then what? The current row, like so. Now, before doing this, I'm just going to go back to ArcGIS Pro right here. Or this one here. And have a look at that. And I'll open the attribute table so we can actually see what's happening here. So I'm going to right click on that attribute table. And there's our N area right here. So I'm going to run my script now. Then I'm going to go back here and close and reopen that table. If it will take it up. And there we go. All those values now are in square kilometers instead of square meters. So that's just to show you that it's working. Of course, the other way to check that it's working would have been quite simply to go back into our code. The other way to know that it worked is to go back in the code, and then you'd have to do another with statement with the cursor. So I'd have to say, okay, with the same thing again, just copy all that down here. Since I can't reuse a with cursor, since it's gone after the update, I have to redo it like that. So that's maybe one time there's a disadvantage with the with statement is that, well, when it's finished running, the cursor's gone. So I can't just iterate over it again. So I'd have to make another reinitialization of it this time. And then then this time print the row. So I'd say print, row 0, like so, to check if it updated it. Of course, it's all updated now, so that check won't work, and it'll just divide these by too many numbers. So I'm going to go back in here, recalculate this. Or why don't I just do this? So we know it's in square meters now. Let's put it back to square kilometers. So up here, we'll go multiplied by 1,000 squared, like so. And then when we print them out, they should all look like this again, right here, big numbers. And voila, it works. Convert it back to square kilometers, run it, and there it works, see? And I'll put it back to what it was originally, like so. So see how quick that is to read and write record values. So attribute values. It's very straightforward. So again, remember that update cursor will not work without specifying the update rows at the end. Now, cursors can also have spatial references. And this is useful in that you may have, let's say, data in longitude, latitude, nat 83, for example. Let me write that better, nat 83. That's an N there. That looks like a W. There, N. So NAT83. And you want to figure out the area of each polygon, let's say. And so you would need to project it, let's say to something like a UTM or MTM. By giving UTM or MTM coordinate systems to the cursor itself, then all the calculations, let's say for area, if you're using the geometry, will be in square meters instead of square decimal degrees, which don't mean anything. So they'll be in a two-dimensional reference instead of a three-dimensional reference. And so cursors are very useful in that regard as well, because you can have a cursor with a different coordinate system than the spatial data layer that you have if you're doing some sort of computations based on the geometry. By default, the spatial reference of the cursor is the same as the layer's reference. So in our case, we're using a modified transverse Mercator zone 9 coordinate system, and that's what the coordinate system of the cursor is. So usually if you're not changing coordinate systems, you don't have to worry about the spatial reference, but you can set a new one to be different. Also, if we're creating a script tool, so let's say we're creating a script tool and we're running that within ArcGIS Pro, which we will eventually learn how to do that, then at that point, the cursor will honor whatever the selection is. So if you did an SQL statement in ArcGIS Pro and then ran your script in ArcGIS Pro, it would only work on the selected records. So you can do that as well. So it honors selections on any of the layers that are involved in your script tool when it's being used. So there's a couple things just to keep in mind to remember. Now, table names are another issue that require delimitation, or validation. So in different types, there's all kinds of different tables, right? So we can have a standalone table called, that just contains data that's ready to be joined to some feature class, as an example. So you might have, let's say, all of the crime in a data table, we call it a standalone table. And then you use a primary key in that table. Let's say crime had by neighborhoods, and there's a neighborhood identifier in the table for crimes. You can join that table to, right? So regular joins, you have a key field, and let's say that's called name. Let's get a better E there, name. And then you have another table, let's say, that belongs to a feature class, and it also has names in it. And these names match something in that table, that row, and then that row. Well, that allows you to join the information that's in the attributes here to the rows of the primary table. Just PT for primary table, and we'll call that the foreign table, FT. So that allows you to do joins and like that, so as an example. So there's many reasons why you would have a standalone table in working with spatial data, because it contains attributes often, and they may not be in the primary table. So tables, when working with tables, you also have to validate their name as well. Because in certain circumstances, you can't have, for example, spaces in the name. So you can have spaces in the name of a shapefile, for example. That's a standalone file, or a DBF file, another type of standalone database file. But in a feature data set, or I should say in a geodatabase, you can't have special characters in the name, like spaces. So you have to validate table names. And that validates basically for any workspace. It will make sure that the name that you send it is properly modified so that it will work or be able to be written to a particular location on your disk. So for example here, if I'm putting something in a geodatabase and I have this as my output field name, by validating it, it will maybe put an underscore for the dot and put then that table into the geodatabase. So you can see that right here. Or in the geodatabase, if you have a space, it puts an underscore so that it fits or is writable to the geodatabase. So different workspaces have different, also have different field naming requirements. So what you can call a field, for example, in a geodatabase, that's okay for a field name, but it will be transformed into my underscore new underscore field in a geodatabase. But that type of a name is not allowed in a DBF. So in a shapefile, you can't have that type of a field name. In a regular folder, for example, that would require you to write a shapefile or a DBF file, for example. And this wouldn't work out. It would be truncated to a maximum of 1, 2, 3, 4, 5, 6, 7, 8, 9 characters. And underscores would be put as well for the spaces in a regular folder. So validate table name, and validate field name are things that you use before writing data to your geodatabase. So let's look at some workspaces. So I'm just gonna make a new one again. So it's clean here, Control A, and I'll just import ArcPy. So I'll say from, or import ArcPy, from ArcPy import env, env.workspace. And I'll just make this to a regular folder, C temp, like so. And I'll make my name here, a name, a table name, camel case. So a table name equals a new table. So let's validate that for the workspace. Valid table name, we can put like that, equals arcpy.validate table name. And then here, because we've already set the workspace, I just put a table name, like so. And I'll just print valid table name, like so. Run that, and it changes a new table to a new table. What if I had some weird characters in there, like a dash new? Is that allowed in that workspace? So I'll run it and see. Nope. Yeah, so that's okay. So I can have something with dashes in it, but not spaces. What about the A, and I have the ampersand symbol there? That's okay as well. A star, I imagine, is also okay. No. So the asterisk is replaced by an underscore. Not allowed there. What if I'm working in a geodatabase? So let's look at ctemp. We'll go back and grab the geodatabase over here for the workspace. Same one we've been using. Like so. What does that look like now? Let's run it. And it doesn't allow dashes or that special character. So it returns a new table. And so you can see the use of this, why that's important before writing something or committing something to which you allow the user to give a name. So often in a script tool, you have an input box for the output file, and the user can choose the name. And they may not know that they can't put certain characters inside of a name. Like they may put that in a new table, and they might think that's fine for the output, but it's going to the geodatabase and it's not fine. So it has to be remade into a underscore new table name, or a underscore new underscore table. Same with the field names. So when you're adding new fields to a particular layer, you must validate the field name, so you add a field which is allowed for a particular data set. And those differ for geodatabases versus shapefiles. Okay, so finally, let's look at working with text files. So a lot of data that you get by, let's say, web scraping or from other people can be text data. A text file is just something that can be opened and read, and it contains alphanumeric characters. For example, here you can see a regular text file in Notepad. And it just has line 1, line 2, line 3, line 4. And it's very common to have to read these files in order to put data into a, let's say, an attribute table using an update cursor, for example, or create an entire new layer using an insert cursor after you create a feature layer. Files like this, text files that have things on lines, are iterable, which is really neat in Python. So once you open a file, it becomes an iterable thing, just like a cursor, and you can iterate forward through it line by line using a with statement. For example, here we have myfile.txt, and it just contains these things. So you can create a file like that in Notepad or whatever text editor you want to use. Just go search, and I type Notepad app like that. And here's my Notepad. So I'll just say, I'll call that line 1, line 2, line 3, line 4. And that could have any number of lines, and I'll just save this. I'll go save as, and I'll put it in my temp folder, C temp. And I'll call it myfile.txt. Out of here. And here, I'll say, for example, with open C temp myfile.txt, comma, as R, I should say R for reading, as file, or is that a reserved word? No, file is fine. Then I could say, okay, for line in file, print line, like so. And see, it just prints every line in the file, line 1, line 2, line 3, and line 4. So I use an open, and here is read, R. The other one is W for write. I could read those in to a list, for example. Let's say I want to put those in a list. Well, I can make my empty list here. I'll just call it out list equals nothing. And then I'll say, okay, in my list, append out list dot append line, like so. So when I run that and I look at out list in my console, it contains these things. Line 1 and \n means new line. So that's the end of line character, that's called. 2 /n, 3 /n, etc. And then all the way to 4. If I want to write those to a file, that's pretty straightforward. I can just say with open, and this will create a new file, C temp output.t, my output, my file out, let's call it like that, out.txt, txt, as W, I should say for writing as W, as file again, and then here, all I have to do is iterate over my list. So I'll say for each value in outlist, value in outlist, here I can say now file dot write, like so, each value. So I'll read it in to a list, and then generally here I'd be often doing something with those values. New values. from the file. And then eventually I could output a new file like this. So if I now go to my ctemp folder right there, I just at the very top, the most recent file, do that and then go back up again. There's my out file. And it looks like that. So all I did was show you how to read in a file, which looks like that, and then output a file that looks the same. So that's called file access, basic file access. So open is always the statement, and you open the file for R reading as F here. In this case, I called mine file when I did the example. And then for each line in F, because that's an iterable, well, that's not good. Didn't write that very well. That's an iterable. So that's an iterable thing, like a list. So I can go over it line by line, printing it or doing other things with it, like I just showed you, putting all those new values in a list that I could then use in the context of other analyses or operations that I want them to be done on. And of course, you could use list comprehension here, like that. Should be, I should have had that there. You need to have the parentheses, print, and then each line for each line in F, and that just puts it right into a straight up list. I did it a long way just to show you as an example. So here's another example. Let's say we have text files that look like this. This could be, you know, the number of international hats for international rugby by different teams in the South Pacific. So Tonga, Samoa, Fiji, Micronesia. So let's say that's the international caps before COVID started for the previous year. So it just means a game against another international team, let's say. Well, I could open them up, get the lines, and then I could even split it into names and numbers, because each line comes in as a single string. So that's my new file, and I'll just make it here in Notepad. And I'll just say Tonga 10. Samoa, that's not American Samoa, that's regular Samoa. Fiji, 7. Micronesia, 9, unlikely. But we'll just say that was it. And then I'll save that, I'll say file, save as new file.txt in my temp folder. So that's my new file. Now here in this example, here in this example, we have our path to the file. We open it for reading as F. And then for each line, we split each line. So I say each line.split, like so, at the space. So that creates a list with 2 items that's stored in vars here. And then for each line, which has now been split into by spaces into a list of 2 things. From that list of 2 things, I get the name, which is the 0 thing, and the value, where I convert the next thing, which is still a string, into an integer. Even though it's a number, it's still a string when you read it in. So it has quotes around it. So you have to convert any numbers to int, for example, or float, depending on the type of numbers you have in the text file. And then I have name and value, which I could then print out, let's say, in some fancy form. So first we'll go back here. And I'll make a new one, just to, again, start from scratch here, so to speak. And I'll say, okay, the file name, I'll use a name like that, file name, equals C temp new file.txt. And maybe I want to make sure I spelled it right. So I could use an argpy function exists. There's other functions I could use, but I'll use argpy. Import argpy. And then I'll just say here, print argpy.exists file name, like so, just to make sure it's there, and I'll run that. True. So I spelled it right, and that file exists. So I could here, instead of that, I could say, if argpy exists, then let's work with it. So I'll say with open file name for reading as F, and then I loop over things. I say for line in F, and here now I can work with line. So I can say a list equals line dot split at the spaces. Or actually, let's just print out the line first to show you what that looks like. So I'll say print line. So print just the raw lines. So you see that each one is a single string. See? Each line comes out as a single string. It doesn't show the quotes on it, but it's a string. Print type line. Like so. So each is a class string. Just to prove that to you. So we want to then split it up for the name and the number of international caps. To do that, first I have to get the line and split it. So I know that it's this would be called a space delimited file. So each line, I create a list. Oops, wrong place up here. So I'll just say current team equals split, or I should say, sorry, a line or line dot split at the question marks. And then I'll just print that to show you. And that's how, this is always a good thing as you're going along. When you try something, print it out to see if it's what you expect. So that's what it looks like. Like so. So if I want to put this component into a string and that component into an integer, so I'll do that on the line here. I'll say str name int caps equals current team 0 and int current team 1. So at the 0 position, of course, is the name. At the 1 index position is the value. And I'll just run that to make sure I don't get any errors. So that's good. And I'll just look at int caps, see what's in there right now, 9, which I would expect at the end of the loop. So now I can print out something fancy or do anything else with these numbers I want to. Obviously, just the print here again represents doing anything else. So I'll use my regular format statement, and I'll say squiggly brace has squiggly brace international caps. Again, cap just means a game in the context of rugby, international rugby. So squiggly brace has squiggly brace international caps as of April 2020. Like so. And I'll put that in a print statement, print that, and then at the end, dot format, which I didn't put in yet, dot format. And then here, I'll put str name and comma int caps, like so. And I'll break that line up. So that continuation character like so. So when I run that now, did I miss something? Yes, I missed the last parentheses. There we go. Tonga has 10 international caps as of April 2020. Samoa has 8. And that would have just been for that year. So I might put from April 2019 to April 2020. Easy to modify, right? And that shouldn't be as of, but between. I'll put had since it's in the past. There. So that's just working with basic input files. And you can imagine then that you could do this and create a brand new shapefile. Let's say you had a file that had coordinates in it and attributes, and it's for points. So you have an X and a Y, and then you have different Z values, which would be the attributes. Well, you could read in the line, split it if it's space delimited, or split it if it's comma delimited, whatever you put in the split statement here. And then open up a update cursor or an insert cursor on a new feature class and start inserting geometries and their respective attributes. And we'll see some of that later on in the course. And we saw writing text files. I showed you how to do that. Now, when writing text files, one thing that's important is you have to remember that when you use the write statement, it writes a string, a straight up string to the output. And you need to ensure that if you want it to be on separate lines, you have to always include in your format statement or concatenate to your output string the \n, and that means new line. Without the new line, all the numbers would just be on one single line, and I'll demonstrate that here. So let's say I want to write out my statement now to a new file. So I'll just go down here. It's frozen here. So back out here to the main line, and I'll say with open, and I'll just give it a hard-coded name here. C. I'll call it rugby.txt temp. C temp rugby.txt. Opening it for writing, so it creates it at the same time as F. And then here, I'll say for, well, I didn't actually save those things. So first I'd have to go back up here, and I'll put a little a list, and I'll concatenate this thing here. Instead of printing it out, I'll concatenate it to the list. So I'll add it to the list. So I'll say a list dot append that statement there. That's good. And then with my new file, for each team in a list, f.write each team. So when I run that, reads it in, it writes out these statements. Now I'll show you what it looks like in temp. There's rugby.txt. Open it up, and everything's on one line. See? They're not separated. I'd have to go in now and manually separate them like that by hitting the enter key. That's kind of a pain. So the way around that, of course, is to add in a new line character when I write that out. So I'll just do this concatenation /n. We won't see it, but that will make sure that everything's on a new line. Run it again, open it back up out here, and there we got everything on a new line. So each line now contains the statement about the number of international caps for each team. So that new line character is very important when you're writing out things to a file. I'm not saying you have to use it. You could simply put any type of delimiter you wanted if you wanted to. But the new line character makes files a little bit bigger, but it then makes it readable and easily brought into other software, such as R, for example, for statistical analysis, or Excel, or anything like that. So that new line character, very important. Now, write only accepts strings, by the way, as well. So this is very important to remember, that the write, if you try to put just a number in there, let's say, it's gonna fail. So when you're writing out a line, it must be as a string. So generally, you should just use your format statement. So format method to write out lines. That ensures that everything is a string. Otherwise, you have to convert any values to strings like that. And the new line character must be put on each string. And there's the format statement example right there. The equivalent for this example here, because they're numbers, just squiggly brace \n dot format. And I don't actually have to put string val in there. I don't know why I did that, but I just need val in there like that. Because in the format statement, it automatically converts any of the arguments that go into, or any of the places that go into the squiggly braces according to the order, automatically converts them to strings. So I don't need the string statement in there. I don't know why I put it. It's not necessary. So for next week, chapters 8 in Zandbergen or 17 in Tateyo-san's, and completing exercise 3, which will give you plenty of opportunity to repeat what you've learned here and apply that knowledge to questions at the end of the exercise.